In the last video, I talked about dropout to avoid overfitting and some of the hyperparameters that we are going to have to tune. This video is going to continue to talk about design choices. Firstly, I'm going to talk about normalization and batch normalization, which again is going to be useful both for regular neural networks and for convolutional neural networks. And then I'm going to go into some of the design choices that we have to consider specifically for convolutional neural networks when we deal with images. So you have probably already seen normalization with Matt, and you've probably seen it in the form x minus the mean over standard deviation. I'm just going to introduce you firstly to a slightly different version that we use for images when we normalize an image before putting it into the network. And all we do essentially is divide everything by 255 because the maximum pixel value that you're going to have in any of your feature channels will be 255 and the minimum is going to be 0. So when you do use this formula, x minus min over x max minus x min, and then this x is whatever pixel you're currently looking at, you're just going to take that pixel, these zeros are going to do nothing to the equation, then you end up just with x over 255. So that's another simple way that we can do a little bit of normalization there. Mostly we're going to be using this sort of thing, and that's going to be especially relevant in batch normalization. So what is batch normalization? The idea here is that when we train weights through this backpropagation algorithm, we actually go from, even if we've normalized the initial training data, by the time we get to the hidden layers, that data has become unnormalized because it's been multiplied by all of these different weights. So the idea is to re-normalize that data after each layer or after every second layer, however often you want to do it. It's up to you, it's a design choice. But the core concept here is that we want to renormalize the data because neural networks train more efficiently and converge faster when the dataset is normalized. And by normalized, I just mean that the data is going to have a mean or an average of 0, and it's going to have a standard deviation of 1. So you'll see this sort of normal curve, and you always want the data to be within this kind of curve. So I'll show you what that looks like on the next slide. So imagine that this is what your data looks like from after the first layer. It looks very, very short and flat. But then the second layer, after applying lots of different weights, well, actually, let's go into this first. We just normalize by taking the mean of this data, which is going to be mu. And for each of these possible points, which are going to be x or xi, we subtract the mean and then divide by the standard deviation. And you'll always get something that looks more like this normal curve that I previously talked about. But then when we put this into the next layer, let's say that it shifts to the right. And again, we've got a problem here. So we just do this exact same normalization again. Instead of having this skewed curve to the right, we can again center the curve around the mean. And then in the third layer, again, this has not only gone to the left, but it's also gone really too far up. So this curve is now, rather than being flat where it was here, it's very sharp and pointy, which again isn't ideal when we want to train. So we're doing the exact same thing. We just change all these values with this formula and get them back to being this nice normal curve. The thing is, maybe we actually benefit from training when it's like this. So batch normalization does one additional thing on top of that. So we are going to say that we go from x, and we're going to do this, take away the mean and divide by the standard deviation. We're going to call this new data point, for each of these individual xi, we call the new data point x hat I. And what we do with this x hat is we actually learn two more weights. So you can think of this as, it's almost like having another layer, but the layer's got only one neuron. So we're going to learn a scale term, this is gamma, and we multiply this scale term by x hat I, and then we also learn a shift term, so the scale term depends on how flat or how pointy this is, and the shift term is going to decide whether it should be on the right or the left. So we just learn these, so we give the network the opportunity to go back from this representation to this one if it feels that it's worthwhile. So we just, rather than forcing the network to do something ourselves, we stay in the spirit of neural networks and allow the machine to decide what is best. The other nice property of batch normalization, which is really, really useful, is if you remember when I first discussed that we need to decide the batch size, we had this idea that we're going to have a data set like this and we're going to randomly sample certain data points. Okay? But what if the sampling, we get really, really unlucky? And what if we end up in the first iteration sampling all of these three? Then obviously, because they all are in this quadrant, these points aren't representative of the dataset as a whole. So we're going to learn bad weights, basically. We're going to learn bad gradients when we do backpropagation because these aren't representative. So what you can think of batch normalization doing is it actually moves these axes over here so that we're back in the right place. So we're moving the axis there, and then we can also take these data points. If we need them to be in a different position, we can. That's what this. What the shift is doing, but then the scaling, we can say actually this needs to go over here, this needs to go over here, this needs to go over here, and now that's more representative of the data set we started off with. It's still not perfect, but it's doing a better job. So now I want to talk about some of the design choices that we can use specifically for convolutional neural networks. And this is going to be more about how the kernel travels across the image and stuff that we might need to do to get better performance. So the first thing that we can look at is the kernel size itself. Typically you would use 3x3, but for some tasks maybe you want to use a smaller kernel size if some of the detail in the image is a lot more focused, a lot smaller. Or if it's much, much bigger, then maybe you want to use a bigger kernel size. The other thing that you can consider is if you have an image which is massive, like 2048 by 2048, and if your dataset is full of these images and you just don't have the computational resources to handle this, then maybe you want to use a larger kernel size, because then you'll have less parameters, less weights that you'll need to learn, which means you'll be doing less computations. So this might be a way that you could sacrifice a little bit of performance, but be able to actually train your neural network much, much faster. So one exercise you might want to do with this kernel size is, just to make sure that your understanding is correct, try to do the calculation of this kernel, which is going to be the 0, 1, 2, 2, 2, 0, 0, 1, 2. Try and do the calculation so that you would get to 12 in this case from the input image. And again, you can try it with all of these in the output feature map, just to make sure that your understanding is correct. And if you have any problems with this, then give me a shout. The next thing is padding. Padding is just where you add a set of zeros around the image. So in this case, we've got a padding of size 1. And all that means is that this becomes a 0, this becomes a 0, this becomes a 0, all the way around. So the reason that we do this is so that we can control the output feature map that we end up with. Ideally, we would have the same size feature map that we started with when we exit the layer, or some like very nice fraction of that feature map. So if we have like 64 by 64 input image, we'd like to end up with another 64 by 64 or 32 by 32 or something like that. We don't want like 57 by 57. So padding is one of the ways that helps us do this. So a question for you is, if we have an input image, and I'm going to use 128 by 128, so this can be an image or an input feature map. If we don't use any padding and we use a 3 by 3 convolution, then what is the output feature map going to be? Second question is, what padding do we need to use with a stride of 1? What padding do we need to use to get back to 128 by 128? So what do we need to add around this image to get back to that number? I'm going to come back to this at the end of the video, so have a think. And a stride of 1 is what I'm going to explain next. So all that the stride length is how far this kernel is going to travel each time it moves. So for a stride of 1, it's only going to move in this direction by 1. So the next feature map, let me change color. The next feature map is going to be, here. And then after another move, it's going to move across a little bit further, like that. However, if we have a stride of 2, then we skip this yellow box and move straight to the orange one. And that's what's represented in this second image. So again, another question for you. If we have a stride of 2 and we've got this 128 by 128 image, and if we have a padding size of 1, what is the output going to be if we have a stride of 2? So stride 2, what is this output size going to be? Lastly, I'm going to talk about max pooling very briefly, because it's not used so much these days. max pooling is very simple, where we pool the data. So we choose a representative data point for different parts of the data. So the one that's most commonly used is this max pooling, where we just split the data into, in this case, 2 by 2, but maybe it might be 3 by 3 or 4 by 4. But we split it into these 2 by 2 squares, and then we just take the maximum. So in this square we take 20, in the next square we take 30, and that's what you get over here, etc. The other thing that you might want to do is instead take the average pooling, where you take the mean of these points. You'll get slightly better performance, but do bear in mind that by doing this average pooling, that's going to take up more computational power, because you have to compute the average of these points rather than just taking the biggest one. So it's a little bit more computationally expensive. But by and large, this has now been replaced. And that's why I asked some of the questions that I did in before. So let's take a look. So firstly, you are going to get, in this case, if we don't have any padding, then you're going to get a 126 by 126 output feature map, which is really not pleasant. So what's happening here is, if we have, let's say we have no padding and the kernel starts in this position, and we have a stride of 1, so the next kernel is going to be up to here, etc. But in this case, we can just see that this is going to be, this 3 by 3 kernel is going to be one data point in the output feature map. So remember how kernels work from the previous videos. So we can think of it as just being the center, and this will be this point here. So for the when we shift across one more and use purple, the kernel is going to move across like this, and then we have this next data point is going to be this one. It's going to correspond. So the entire kernel multiplies by all of these 3 by 3 parts in the image, and it's going to just make this one point in the output feature map, and then eventually we're going to end up with just the 3 by 3. So that's why we add the additional one padding layer, because if we do that, then now this 3 by 3 is going to correspond to one point in the output feature map, and this is going to be here, and then once we move across, it's going to be this point, etc. So we get something which is the same size. So you'll often see padding size of 1 when we're using a kernel size of 3. So if we know now that when we have this padding of 1, that if the stride is 1, then we get a 128 by 128. Hopefully you can see that if we skip across a little bit more, rather than just skipping across one time, we're going to do half as many computations. So we're going to end up with this very nice 64 by 64 output. And this is actually the reason that max pooling has stopped being used as much, because the whole point of max pooling was to get from an n by n feature map to a n over 2 by n over 2. But why bother doing that when you can just use this stride size of 2 and actually learn directly from the feature map, rather than doing this slightly weird pooling operation and losing some information. So that's everything for engineering neural networks. I will see you in the next video.